Okay, so ladies and gentlemen, I've asked you to call up this, this model. We're going to be first explaining some basics of the approach we're going to be using. It's the infectious disease nonlinear model, and we're going to use it to illustrate some of these types of uses to which dimensional information can be put. So if you'd like to just open it up, you can have it here, and we'll come back to it in a few minutes here. In the meantime, I'd like to introduce to you the subject here we're going to be talking about, which is dimensional reasoning about models. Using information about the physical dimension involved for a couple of purposes. Purpose one, to identify problems within the model. Often subtle problems that would not be evident immediately, but which will turn up through dimensional analysis. Secondly, to be able to reason about what model formulations need to be to make sense. Thirdly, to be able to reason about how model behavior will vary as you change certain quantities in the model. And fourthly, to be able to build reduced scale models of that with 50,000 agents might give you an understanding of how the model would behave with 50 million agents in a principled way. Okay? So we're going to be providing a brief introduction to this. I'm not going to be able to hit all four of those topics other than to, for some of them, note what's possible. So within today's lesson, we're going to be talking about some basic concepts associated with dimensional analysis and the notion of dimensional systems. We're going to provide some examples in discussion. As part of this, we're going to be taking this model that we have already and modifying it to incorporate dimensional information. Okay, couple of motivations. Dimensional analysis, this technique of reasoning about the physical dimensions associated with the system, things like time. This variable has something to do with dollars per year. This other variable has something to do with the number of persons per week. That sort of reasoning has long been a feature of science. You see it a lot in natural sciences such as physics, and in certain certain disciplines within engineering. And for centuries, it's been a staple of teaching in certain sub areas of the technical community, but it's very little appreciated within many of the people who operate in the computer science area, or for that matter, who build the sort of models we've been talking about in the course of this semester. It's only a sub-community of that. And they've only made limited use of dimensional analysis. There's a lot of benefits that dimensional analysis brings to the table when leveraged properly. And we're going to focus on just the first couple of these in this lecture. Spotting models that are nonsense and avoiding mistakes, and thinking through how certain formulations need to be structured. A critical one I want to draw attention to, though, because it's very practical, even for the sake of exercises such as the one you're pursuing with the last problem set in problem one there with calibration. Proper use of dimensional analysis can often, not always, but often reduce the number of parameters you need to vary in a sensitivity analysis or a calibration experiment. It can take it from calibrating with 4 parameters to calibrating with 2, for example. You're getting the same information, but with much greater computational economy. And also at a very practical level, creating models with small populations that can be quickly simulated to understand behavior of models with larger populations. Okay, but let's go to some basic foundational concepts here. So I'm going to distinguish two terms that are often interchanged. Even any logic interchanges, unfortunately. The first of them is the notion of dimension. The second is the notion of unit. Okay. Dimensions the term dimension refers to the semantic category of associated with a variable. So for example, we might say that this is a variable that expresses the length of something, or this is a variable that expresses an acceleration. This is a variable that expresses a count of people. This is referring to the type of domain to which it refers, to the category of things. Maybe it's a simple one like length, or maybe it's a compound one like length per unit time. In other words, velocity or speed. But the point is that it refers to a broad type of quantity. You'll notice I didn't say length per second. I said length per unit time. I didn't say meters per second. Meters per second is an example of a unit. Length per unit time is an example of a dimension, because it's not specific about the units. It's not specific that length is measured in meters as compared to kilometers, as compared to miles. It's rather a general type of information. So it's a length. And it can be described by many particular yardsticks used to measure it, which is the focus of units. So dimensions are independent of size of measure, even if we can measure it. So we talk about time, for example. It's not referring to a particular measure of time. And generally speaking, you can't take a variable in one measure, length, and convert it by multiplying it times by a number, convert it directly into a variable for another dimension. It's a different sort of thing. So you can't take a length and make it a square of length, or an area. It's a different type of quantity. By contrast, units describe references that are used in performing a particular measurement. They describe the yardstick or the meter stick against which you measure a quantity. So for example, if something is of dimension length, we might measure it in terms of meters, furlongs, fathoms, might measure it in terms of miles, inches, centimeters. Units describe the point of reference by which we measure this item, whereas the dimension is the more fundamental semantic category associated with it. So if we have a time, that's a dimension, and we may measure it in microseconds, in weeks, or centuries, right? Both cases, we're talking about metadata, data about a particular number. So a number 1 might represent something that is measured in meters, a length in meters. It may indicate 1 meter, or it may indicate 1 centimeter. But that 1 could represent, if it's not documented, it might in some cases represent instead time. If we don't have that metadata, we're not sure what that number means, what it refers to, what it indicates in the world. And both dimensions and units are types of metadata about quantities. Units are more specific metadata. They have to do how is it measured, or against what yardstick was it measured. Okay. All units relate to a particular dimension. So these 3 units here, these are all units for what dimension? Time. Meters, centimeters, miles, inches, those are all units for what dimension? Yeah, distance or length. Sure. For units, we can convert by simple multiplication by appropriate dimensional constants. So for example, we might have something measured in centimeters and we want to convert it to inches. So we divide it by the number of centimeters per inch, right? It's quite straightforward that we convert from one unit to another. Where we have something that's measured in milliseconds, like units time, and we want to convert it to seconds. We multiply it or we divide it by 1,000, right? We'll come back to where those numbers came from, but that's the general idea behind them. So we can express a given quantity in only one dimension. It only has one dimension associated with it, one semantic category, time or length, but it could have many units associated with it. We could express it, or I should say we can express it in different units. We could say this 1 meter is instead, about 39 inches or what have you. So we can re-express it in many units. And well, we'll come to dimensionless quantities in a second. So here's some examples of units and associated dimensions. So you might have a dimension of 1 over time. This is a measure of frequency, how quickly something happens. And its units might be 1 over year, 1 over second, etc. Distance, we can measure, say it's of dimension length, but we could measure it in different ways. Something like an angle has a very special dimension. We talk about its dimension being unit or dimensionless, less accurately, being of unit dimension. But we could, in fact, quantify it in radians or degrees. Okay? So we as humans have invented dimensional systems. We've chosen dimensional systems. And those, in your physics courses, you will have encountered probably one or more dimensional systems that are quite standard. Right? Give me a dimensional system you might have used in unit and in physics class. What's a dimensional system?
Velocity?
Okay, so velocity is a dimension, and a unit system, a dimensional system will actually specify units by which to quantify velocity as well as others.
Like SI?
Yeah, exactly. The Système International, or the MKS system for quantifying units. These systems have certain ways of measuring pressure or certain ways of measuring distance associated with them. Okay, we're not going to get into them, but there's published standards for how we characterize quantities. Now, let's talk about these things, these dimensional quantities. When we have a quantity that characterizes some information about the world, we can often express it with some dimension and often with particular units. We're going to focus here on dimensions for the moment. And often we're going to have an ability to express it in terms of other dimensions. So we might have, for example, cash flow we're interested in. And this might be, currency per unit time, for example. Or we're interested in office space costs, so currency per area per time. So we talk about, what's the going rents in downtown office space here in Saskatoon. It's maybe, $200 per square foot, or $200 per square meter, or what have you, per month. Rate of water flow, the water flow of the South Saskatchewan River out the windows there. We have some amount of volume per unit time. These are dimensions associated with that rate of water flow, okay? And we can typically specify for a given unit a clear dimension associated with it. Now the interesting thing is that when we express these dimensions, we can do so reliably by expressing them as a product of powers of underlying particular dimensions. So for example, cash flow, currency per unit time, we we can express that as currency to the 1 power times time to the minus 1 power times, well, these are some other people and length to the 0th power. By the 0th power, I just mean there's no dependence on that. There's no term involving that. So you could think of it as 1, a dimensionless sort of multiplier. So this is the effective dimension. Okay. Incidence, people per unit time. Regardless of whether it's tens of people per week or per person per year, those are different units associated with person per time. We could express as p to the 1 times t to the minus 1. T to the minus 1 reflecting the fact that t is in the denominator, p being the numerator there. Okay? So we can express dimensions in general as products of powers of particular dimensions. Yeah? Alternatively, we can take those and we can represent them in a vector space, okay? We could put it something like this. So, for example, if we have something that's length per second squared, or length per unit time squared, we might express it like this. So we have powers of time, minus 2, powers of length, 1. Okay? Length to the first power here, and time to the minus 2 power there. So something like gravitational constant g might be expressed in that. We could express other quantities accordingly. So this is length squared per unit time squared. Okay? So here we have a dimensional space we've illustrated. Alternatively, we could think of it like this. A given value, 3, might be describing a quantity, for example, that's dimensionless. So that same number, 3, in a variable in the computer might be expressing a length. And we can characterize this by placing a dimensional grid where essentially the position along this axis down here indicates length, the power of the length dimension, and up here the power in the time dimension. So something like a pure length involving no component of time, where time is to the 0 power, lies on this axis at this point. Velocity, meters per second, involves 1 step out in length and minus 1 in time. Here, that's because the time is to the minus 1 power. And the length of this vector here would represent the number. So maybe it's 2 meters per second, right? So it follows along there. So we can illustrate these dimension quantities not only with the number 2 that's in the variable, but with the metadata associated with it, with the data associated with the underlying dimensions. Okay? So this may seem prosaic, but it gets very practical. So this was about dimensions, characterizing things at a dimensional level. Let's talk about units, okay? So it turns out that if we conceptualize them like this, we think about the powers involved, these powers here that are illustrated, okay? That can help us recognize how to convert between these numbers associated with quantities, okay? So let's consider 2 different measurements. One of them is expressing dollars per linear foot, okay? And suppose we want to turn this into dollars per meter. So we have some lumber perhaps, and we talk about it being priced at, $10 per foot, and we want to convert it into how many dollars per meter. What would we need to do that? So, okay, maybe I'm talking about conduit, and you tell me, it's $1 per foot, and I know I need, based on my measurements, I need to buy 3 meters of that. What do I need to do to convert it into an amount of money? I need to figure out how much is it per per meter, right? How would you do that? $1 per foot, and I want to convert it into dollar per meter in order to then figure out for 3 meters how much it's going to cost. What do I do? Yeah, multiply by feet per meter. See that, right? We have dollars per foot, which is $1 per foot, and we multiply by how many feet per meter to yield this to yield the number in dollars per meter. And then if we have 3 meters, we multiply it by 3, right? Great. Okay. So here we've converted dollars per feet to dollars per meter by multiplying times 3.2. What would the situation be if I had a number that's dollars per square foot? Maybe it's the monthly rent or something. And I want to convert it to dollars per square meter. What do I need to do? What would I multiply it by? Would I multiply it by 3.2? Think about it. So I have something that's in dollars per square foot, right? Here we are. Dollars per square foot. And I want to convert it to know how much it's going to be as expressed in dollars per square meter. What do I need to do?
Convert from square feet to square meters?
That's right. I have to reason about square feet to square meters, right? And in order to do that, ladies and gentlemen, I need to reason about how many feet per meter, right? How many feet there are per meter, but then I need to square it, right? Think about that, right? So if this is, this is $1 per square foot, and now I'm dealing with a square meter, right? Something like that, and I've got, okay, I'm not a very good artist, but you'll forgive me. It's a computer science course. So we have something along those lines, right? If I want to figure out how many dollars there are per square meter, I take dollar per square foot, and I need to multiply it not by 3.2, but by 3.2 squared, because I need to figure out, okay, it's how many feet per meter. I need to take that, and I need to square it, because I've got it in 2 dimensions, right? And that will give me, okay, this is, the equivalent is $10.764 per square meter. Okay? This 2 up here, this 2 in the exponent reflects the fact that this is in square, it's associated with the square of that dimension. So the fact that we have a dimension here associated with this original quantity of 1 of money not per length but per length squared is what led to that square in the exponent there. That square in this feet that ends up squaring the feet per meters. Okay? So it turns out that these exponents here, the exponent associated with a given quantity, like length, tells you by what term you have to multiply those values to convert from one length to another. The fact that this term is dollars to the 1 tells me what would I have to do to convert from US dollars to Canadian dollars, for example. I don't have to end up squaring that, it's just to the 1 power, okay? So the fact that we have this square here means we have to square this conversion. The fact that the length measure is associated with a 2 power in its exponent means that when we convert from one length measure to another, one unit of measuring length to another, we need to square the appropriate number, okay? Do people get that? Okay. Now, a key factor that is going to be one of the most important points of this lecture and its practical implications for more sophisticated use of this sort of modeling is the following. If the dimensions of a quantity do not depend on a different dimension, if it is dimensional power, an exponent of 0, it's invariant to changing that dimension, okay? It doesn't matter what our unit systems are for that dimension. It's not going to change the number, okay? So let's give a trivial example of this that just seems so obvious to not even be worth mentioning. Think about a board's length. A board's length can be quantified as length times t to the 0 power. And if I choose to quantify time in seconds versus years, it doesn't matter. The length doesn't change as measured, right? It doesn't involve time. Time is not measured as part of it. It's not part of the equation in terms of the powers involved. So it doesn't matter. But the key component of this is that there are quantities that are called poorly dimensionless quantities, or quantities of unit dimension. To talk about them being dimensionless, that's the most common term for them, but it's an unfortunate term. It's kind of like saying something of length 0 is lengthless. Well, it kind of is lengthless, but really it has a very particular length. The length happens to be 0. And so it is with dimensions. So something of unit dimension, to say that it's dimensionless is not quite accurate. It has a very particular dimension. It's the unit dimension. It's associated with 0 powers. So I'd like to give you a couple examples of unit dimension. Okay? This slide is going to remain up on the screen for a certain fraction of this lecture. Maybe it's 5% of this lecture. If we measured this lecture and its length in seconds, in minutes, or perhaps for some of you who would love to get out of here and love to get out of this bad air quality in years, it doesn't matter. The fraction of time of this lecture that this slide is up, 5%, it's the same, regardless of whether we measure the length of the lecture in seconds or years. You can measure it in centuries. It doesn't matter. It's 5% of the lecture. That's a dimensionless quantity. We could change our units for measuring time, length, whatever. It's not going to change that. If we asked what fraction of this table is occupied by my tablet, maybe it's 10%, no, it's not 10%, maybe it's 5% of the table. That also is invariant to how I measure length. If I say I'm going to measure this table as square meters, or if I say I'm going to measure it as square kilometers, I'm going to measure it as square light years. That doesn't change what fraction of the table is occupied by my tablet. That's a dimensionless quantity. What that number, so the number associated with that is a special sort of number. It's a number which doesn't matter our choice of unit systems. Another dimensionless number would be a probability. You talk about flipping coins. What's the probability it turns up heads? I don't care if I quantify coin flips, it's thousands of coin flips, or single coin flips, or millions of coin flips. It's this, as long as it's the same in the numerator and denominator, they cancel. It's the number that turn up heads in the numerator, and the number of heads in the numerator, and number of heads in the denominator. Oops, number of flips in the denominator, right? And as long as these are measured in individual coin flips, or in tens of coin flips, or thousands of coin flips, or millions. So if 1 means 1 million in the numerator and the denominator, so it's 0.5 in the numerator, and 1 in the denominator for a million coin flips, it's the same. The units cancel. So that's a unitless quantity in popular parlance, but it's better called a unit of unit dimension. Okay. Do people get that concept? This is a special class of things that are unitless, that are dimensionless. Again, poor names, they're of unit dimension. They have unit dimension. They are invariant as to how we measure things. We don't have to worry about our measurements for things, our measurement systems in these numbers. People get that? Okay. Those sort of quantities are extremely important in modeling. Why? Because, ladies and gentlemen, when we characterize processes in the world with a model, this again is one of the most important statements of the whole lecture. If you get this, you'll get one of the most important points in the lecture. One of the most testable points, too. Why are these quantities so important? Because in modeling, we are trying to characterize processes in the world. And ladies and gentlemen, the world does not change its behavior if humans adopt different unit systems. What that means is that processes in the world must be describable, you must be able to characterize them. Whatever the equations that govern them, they have to involve dimensionless quantities. They have to be subject to description purely in terms of dimensionless quantities. Otherwise, when we switch dimensions, the behavior of the world will change. So whatever systems are out there in the world, they must be subject to description using only dimensionless quantities. We must be able to characterize them using purely dimensionless quantities. Okay. Okay. So let's talk a little bit about this. So we had noted before that the dimension associated with a number within a dimensional product here, like dollars times feet to the -2, that those numbers in the exponents dictate how you have to, by what constant you need to multiply them when you change dimensions. When you change from feet to meters, for example, by what number do you need to multiply this 1 to get feet per square meter? Well, it's 10.76 because it's this squared and y squared because of that exponent. So with dimensionless quantities, what we have is quantities that can be expressed as a product of dimensions whose exponent is purely 0. Okay, so over here we saw these set of quantities here. But if we're thinking about a probability, it would have, for example, all of these exponents be 0. If we were talking about the fraction of the area of this table occupied by my tablet, we're talking about something where all the exponents are 0. Okay, the units cancel is another way to say it. Okay, so in short, when we switch from one to the other unit systems, we multiply by that to the 0th power, and a number to the 0th power is what? 1. So, in short, we multiply the number by 1, and we leave it unchanged, therefore. So these quantities are independent of unit systems, okay? So let's talk about, one of the bigger modeling points coming out of this lecture is that however we describe systems in the world, they have to be amenable to description using dimensionless quantities alone. And physicists have, for centuries, routinely described, when they characterize systems in the world, they routinely do so with dimensionless models. So they start with a model which is described in a dimensionless way. Okay, so instead of dealing with the count of susceptibles, the count of infectives, what they would deal with is the fraction of people that are susceptible, the fraction that are infective, for example. And they prefer to state a model in those terms rather than in terms of the actual counts of people, because their characterization is dimensionless and therefore invariant as to how we measure things. But in the rest of science, there isn't that routine use of those sort of models. We may come back to that point. Okay, the first thing I want to talk about, though, in terms of how this dimensional analysis can help you model, is by talking about preventing common mistakes, okay? And I referred to this earlier in class, so hopefully these are concepts that you'll have some appreciation for. Now, in the ideal world, you'd already have internalized this. So here we have a stock, and here we have a flow into the stock, right? The flow here has to be, in terms of dimensions, whatever the dimension of the stock is, the dimension of the flow has to equal the dimension of the stock. I'll denote that with brackets around it, divided by time. Has to be. Why does it have to be that? Well, remember, ladies and gentlemen, and remember especially at the final exam, that this stock is the sum up of this flow over time. But this flow is people per unit time, and so this stock is actually summing it up. We write it as x of t as an integral from the start of the model to the current time of the flow, and I'm going to do it as an integral over, let's say, tau, times d tau here. This is some unit of time, or this is some small bit of time, and we're multiplying by the flow. We're totaling up the flow as it occurred on a per day basis, let's say, multiplied times the length of the day, and we're summing that up. That's what this integral is. It's a sum up of these terms. And you could think of it as kind of an approximation, or being approximated by this, delta tau. This is a delta, small step. What's the dimension of this guy here? Well, the dimension is f. I mean, that's whatever the dimension of f is. And the dimension of this guy is what? A delta of something that's measured in time is what? Itself measured in time. It's time, okay? So delta t, time is advanced by 1 day or 1 microsecond or something. So this is of unit time. And as a result, x is of units, whatever unit of f is, times time. And I would argue that's why f has to be that, so that this guy over here is the dimension of x. The fact that you have this relationship here implies this, the dimension of f is just the dimension of x divided by time. So if this is persons, this has to be persons per unit time. If this is dollars, this has to be dollars per unit time. And depending on your time, maybe it's weeks, maybe it's days, but mutatis mutandis, it'll be corresponding thing. Does that make sense? This is a stock. The flow, it's got to be the units associated with the flow or the units associated with stock divided by the appropriate unit of time. Okay. Sounds like people grok that. At least many people grok. I appreciate your grok. Okay. Okay. I think I'll skip this except to say, if we're interested in the dimension associated with a quantity, there's many ways to sort of probe this. If we're interested in how to quantify something in a model, what are the dimensions associated with it? We might ask, well, if we were to change our unit system, for example, how would this quantity change? Is there another value which it can be converted from that we can reason about its quantity there? Okay, so let's talk about computing with dimensional quantities, because this is going to get into the use of any logic. Ladies and gentlemen, when we are reasoning about a model where it has dimensions defined, we can think about the model operating as normally in terms of the numbers in the model. But each of those numbers is associated with a dimension. you may have two variables that hold the values 1 and 2, and you add them together. But if those variables are not in the same units, and if they're not in the same dimensions, your model has grave problems. So if you have a value in your model that indicates 1 meter, and you have another value in your model that indicates 2 feet, to add them together is numerically possible, but semantically meaningless, right? You get 3 out, but it doesn't mean anything because it's not dimensionally consistent. Do you see what I'm saying? 1 plus 2 there is not equal to 3 because 1 is in meters, 2 is in feet, and suddenly you don't have a meaningful addition because they're an incommensurate unit. So what do you do in that case? You convert the units, great. But suppose you have people, so suppose 1 is number of people and 2 is time. Does that make any sense to add a person to time? No, it is semantically meaningless. Your problem there is not one of unit conversion, as grave as that is, as serious as that is. The problem there is that it's semantically meaningless as a instruction to do that. So ladies and gentlemen, both of these are common flaws. There was a famous space probe that went to Mars some years back. Not the most recent failure, but it was an earlier one. I think it was the Mars Explorer, but I can't remember the exact name of the mission. It was multiple billions of dollars, I think, as a mission. And it was a failure. It exhibited problems in the descent phase, I think, and crashed into Mars at high velocity. And massive amounts of years of very careful labor and work was lost. And a great deal of scientific exploration possibility was lost. And it was lost because of a failure to convert units properly. They had units on the one hand that were measured in, maybe it was MKS system, and the other hand measured in NSI, and they at some point combined them together by adding them, and it led to a meaningless number that was used to govern the thrusting of the thrusts on the rocket, and it failed to decelerate properly and was destroyed. Dimensional quantities are key, and when we characterize things in our programs, regardless of whether it's a model, I mean, my gosh, some of you are in the database course, aren't you? 355? We're in the database course? What's that? Okay, well, I'm sorry, but in the database course, you are also describing quantities in the world. You are describing counts of, what is it, of museum artifacts or something? Yeah. And you are characterizing perhaps weights of quantities, etc. And once again, we have these numbers, and if those numbers are disconnected from the units, and we're not careful about how we treat those, we can get meaningless units out. So this metadata is often just about as important, arguably more important, than the numbers sometimes. The numbers themselves are often valuable, but if the numbers aren't coupled with meaningful metadata, there can be enormous problems, and you can do something silly that's meaningless and get something out that seems meaningful, but actually carries no real value. Okay? So when we're computing with dimensional quantities, when we're adding together a quantity, when we're dividing quantities, we can conceptually think of that occurring with the dimensions as well, right? Conceptually, we can add the numbers and then add the appropriate units or dimensions that are carried with it, and potentially spot issues. So, if we had something like this, suppose we have A being persons, B persons per unit of time, C time being in time, and D being dollars. Here we can perform the operations conceptually, not only on the numbers associated with them, but associated with these dimensions. So when we add together, for example, two persons, we get a person out, right? When we multiply a person per unit of time times time, we get a person, right? Right? Familiar stuff, almost goes without saying, but the point is, when our programs are operating, there is kind of a parallel logic for dimensions which has to hold, which has to hold water, which has to be consistent, or else our programs and our models are meaningless, okay? So one of the key things that you can do that's meaningless is adding together quantities whose dimensions differ. It's meaningless and carries over to subtracting quantities. After all, that's just adding a negative version of the quantity, right? If you add people to people per unit of time, it is meaningless. Now this may sound obvious, but believe me, it's one of the most common mistakes modelers make. And even very experienced modelers can even sometimes fall into this at times. They'll do something like add a stock to a flow. Sounds reasonable. I mean, after all, the two variables in the model, you can add them together. And if you do that without a little bit of work, any logic will let you do that. X plus F, sure. Here's the number. But it's not sensible. It's not sensible because you're adding things of different dimension, ladies and gentlemen. You're adding things which would change dramatically if you were to change the time by which the model operates or what have you. So that's an example of adding things together. Its dimension is different. And it's an extremely common mistake. Or you say, X minus F. If one of the most common things here is you have, this happens a lot, you have F flowing out of X, right? F flowing out of X, and you say if X minus F is greater than 0, then F is at its full value or what have you. Maybe that's in the formula for F. And it doesn't make sense. I mean, this is meaningless. X minus F is meaningless. We're taking something people minus people per unit time. It's not a sensible value. It's not a sensible thing. It has no units associated with it. But an exception of that is, ladies and gentlemen, if you have something raised to another power, let's suppose you have exp of some value x. What does the dimension of x have to be? Well, does anyone remember the Taylor series expansion of x? Anyone remember that Taylor series? Well, good. 1 plus, excellent. Plus, yes. And maybe I'll write it as x to the 1 over 1 factorial, right? Plus x squared over 2 factorial, right? Etc., right? Right? Or factorial just means, well, most of you should know what factorial is, right? This is 1, 2 times 1, and then there'll be 3 factorial. And if x is not dimensionless, what does that mean about this? So suppose x is in persons. What's the problem?
You're adding 1 to persons.
Okay, and then to persons squared to persons cubed. It ain't gonna work. It ain't gonna work. So if you have an x of a number of persons, there's a problem in your model. There's a problem. At the least, you need some sort of constant that's going to lead the product. It's going to be a per person thing that you multiply by it. And that's really important because the value of that constant will change if you, in the implausible case, you decide you're going to measure persons and thousands of persons or what have you. So in short, if this is exponent of time, that doesn't make sense either, because if we measure time in seconds versus years, it's going to totally change our relationship. So we need a constant in front that reflects that. Yes? Yeah. Oh, okay. Okay, so ladies and gentlemen, as I noted, adding things of different units but the same dimension, adding something measured in meters to something measured in feet, it's semantically sensible, but it's numerically incorrect, right? One meter plus two feet is meaningless. I mean, it's semantically consistent. Sure, I'm adding lengths, but it's not numerically meaningful. Meanwhile, if I add these things up here as say a length to an area, that's semantically meaningless. What does it mean to add a length to an area? Or what does it mean to add a person to a time? It doesn't make sense. Makes sense to divide person by time, persons per unit time. The number of people that are leaving this room per second is low, but non-zero. That's a meaningful thing. Okay. Common modeling errors that are dimensional errors. Setting the value of a flow equal to the value of a stock. Subtracting the flow from a stock. Comparing a flow and stock. Is F less than X? For a flow, multiplying it, multiply the value of a stock by a time constant. Remember, I tried to develop intuitions with these, right? So if we have an average amount of time in the stock and we have a first order delay, the flow has to be the stock divided by that average time. Why? Because because the flow times that, because the flow has to be of units, the stock, over the units of time, right? And the same thing with the hazard rate is likelihood per unit time. Okay. I'd like to talk about this in any logic. So here's this model, right? Here's our model. We built this model back in the fullness of the fall, before the weather turned bad and the air quality plummeted. Believe me, I got FMD. FMD is working to improve the air quality here. We've sounded the alarm. So ladies and gentlemen, here's our model. You'll notice in any logic that we can specify the numbers here, and that's what we've been doing, right, with these sort of models. But take a look at this. Go down to the advanced area. You'll notice in the advanced area, there's a place to put in units. Do you see that? You see these system dynamics units? Yeah. So ladies and gentlemen, within this context, you can actually go and enter units in to specify the units associated with different components of the model. Okay, this is an extremely important part of the interface. So I'm going to suggest thinking about this. Okay, now a physicist would approach this a little bit differently. They would say, look, let's just get rid of a lot of this issue of inconsistency by having it be fraction susceptible, fraction infective, fraction recovered. What would those units all be? Well, the units, if this were the fraction of the population susceptible, what would the units be? Dimensionless. It would be unit dimension. If it were the fraction, because, well, think about it. It would be people over people. And however we measure people, whether it's per person, or per tens of people, per 100,000, this is quite common in the health sciences, whatever units you measure these in, the units are going to cancel. So it's a dimensionless quantity if it's a fraction. So from a physicist's perspective, they would do it in fractions, but you'd still have to specify some meaningful unit there for, or some non-unit dimension for new infections. Okay, so let's do that. System dynamics units. I'm going to say person for susceptible. And similarly for infective, we're going to say person. And for recovered, we're going to say person. Okay? So that's a good start. Now let's start getting down to the flows. So what does the flow have to be here? What's the dimension, not the unit, but the dimension of this flow? Person over time. And in fact, that's how AnyLogic likes to phrase it. Person per unit time, okay? So that's the units associated with that, and similarly, the units associated with this, okay? Great. Now, I noticed before coming here that my my version of AnyLogic seems to have somewhat inconsistent support compared to previous versions here. But if you go up to Tools and you say Check System Dynamics Units, it's going to say, okay, a certain number of problems found, and it's going to warn me of some of them, but interestingly, not all of them, okay? So here, ladies and gentlemen, it's saying, for example, actual unit here, person per unit time differs from, okay, so given person per time. So it looks like it wants us, now that's a pain, it wants us to specify it as lowercase time, okay. So let's just try that. Okay, oops, I didn't want to build, I wanted to check the units. There we go. Okay, so it's complaining about this one as well, and for some reason it is still focused on, what's that?
Does it want the spaces in between
Maybe.
Wouldn't the stock just be persons?
It is persons, isn't it?
Well, you're doing. Oh, sorry, we're on that.
Yeah, it was showing it in a weird way. You're absolutely right though, Andrew. It was showing it in a weird way. When I clicked on that, that was what was selected, but that was not shown. Okay. Okay. Yes. So is yours showing the same? Oh, it does. Oh. Okay. I thought I changed that, but thank you. There we go. Boom. Okay. Well, that's great. But it's still saying there's two, and there's nothing shown here. Let's. Yeah, I think that's a bug in that version. Okay, so let's go here. Duration of infection. What are the units associated with that? Duration. What does it sound like? Duration. Okay, days. So in dimensional terms, it's what? What's the general type of thing? Time. It's a time, ladies and gentlemen. Now, let's reason about that. Well, it's going to reason about it for us. But the flow is infective divided by this, right? It's got to be time. Yeah, this thing is divided by time. Great. Okay, so we could continue to do check. Okay, problems found. Okay, it looks like that made it a happy camper. Now let's go to the force of infection. I think I understand why it's showing these kind of spurious errors. Okay, let's go to force of infection. What's the unit associated with that? Well, that's a hard one. Let's start with the things that contribute to it. This is actually very important. It's got to be something based on several things, but let's go to total population. What's the unit of that? Total population needs to be person, right? I mean, after all, if each of the things it depends on, it's just adding them together. This is person, right? Okay, that's great. How about fractional prevalence? The fraction of the population that's infective. What's the unit of that? It is what? Unit dimension. Okay, I'm going to say 1. I actually, to be honest, I don't actually remember exactly how that's phrased. I think you just say 1 here, but we'll see in just a moment. Great. Okay. So that's the fraction. why is it dimensionless? Well, look, if we measured people here as hundreds of thousands, if one in susceptible meant 100,000 people, one infected meant 100,000 people infective, total population is going to have that same thing. One there will mean 100,000 people. And the fractional prevalence just is one divided by the other. Units cancel. Whatever persons is measured in, it cancels. You could alternatively write this if you wanted to be, very specific. You could say person per person. But the point is it's dimensionless. It's independent of how we measure persons or time or length or all those things. Yeah? Okay, let's go to let's go to mean contacts per hour. Okay. Okay, I like that. I like that. It turns out that it's a little bit misleading in that, because it turns out this is persons per unit time per person in the population. So it turns out it's 1 over time. It's a frequency of contacts. It's like 50 contacts per hour. So number of contacts per hour. It's a per hour or per day value. So it's actually 1 over time. Okay?
Put it in the spot.
Oh. No, this is mean.
Should be in system dynamic units.
Oh, gosh. Oh, wait a minute. Yeah, thank you, man. Okay, great. Ladies and gentlemen, I'm grateful for your paying attention. System dynamics units, okay? Mean infectious contacts per hour. What is this going to be? What has this got to be?
The same thing.
Same thing. Why is it the same?
Because it's 1 time.
It's 1 times it. Yeah, so this is 1 over time, ladies and gentlemen. 1 divided by time. Yeah? Okay, let's go with this probability. This probability of transmission per contact. So if 2 people are in contact with each other, one's susceptible, one's infective, what's the chance that it will, or what's the unit associated with the probability? 1. 1, ladies and gentlemen. It's unit dimension. Doesn't matter if we're talking about, 1,000 contacts occurred, and we're measuring that in thousands or ones. It's going to be the same. It's invariant for that. Okay, now we come to the final thing: force of infection. What does its units have to be consistent? Well, it's whatever this is times whatever that is. So this is 1 over time. This is 1. What do the units of this have to be? 1 over time. Which makes sense, because new infections is susceptible times this force of infection. New infections is person per unit time. So force of infection needs to be per time for it to when multiplied by susceptible, yield that thing. Okay, so let's try checking the units. Check performed, no problems found. Let's see what would happen if we did something strange. Well, I know, maybe you think the entire class is kind of like that. But let's go up to mean contacts per hour, and let's change it to persons per time. Okay? What would happen then? Now it's an unhappy camper. And it says actual time 1 over time differs from estimated persons per unit time. So it's telling you, wait a minute, to be consistent, 1 over time, this has to be 1 over time, but you've told me person over time. So it's telling us that there's an error here. So is your software working the same as this? Okay, good. So ladies and gentlemen, checking the units is a good test for a model. Your model can be full of sound and fury, but unless it's dimensionally consistent, it signifies nothing. Shakespeare said it first. although he didn't have dimensional analysis in mind, presumably. Okay, ladies and gentlemen, so dimensional consistency is extremely important for model correctness, but more than that, ladies and gentlemen, it's extremely important for program correctness. If you leave here and you never perform a simulation in your life, although I'll tell you, lots of things you interact with will secretly be performing simulations for you. But if you never perform it again, but you're a software engineer, it's worth thinking explicitly about dimensions and about units. And my prediction will be, it won't be that long before we actually track them more consistently for software engineering. Okay? Time is running short here, and I do want to make a few closing remarks, even through the smog. But I want to indicate once again and emphasize that what we've seen here is just a small piece of the use of units. A lot of their use historically, and use still that's helpful in modeling, is thinking through from first principles, from the dimensions involved, what the units associated with certain quantities in the models have to be. An example is the predator-prey model that you built. Gophers and coyotes. You saw in that model oscillations. Do you remember them? How could you forget? You know, remember it was cycling? We had gophers going up and coyotes following, and then coyotes would go up above the carrying capacity, gophers would tank, and then coyotes would come down. And those were oscillations. And the question is, okay, given the model specification up there, what's the frequency of these oscillations? And it turns out that by reasoning from first principles here, reasoning about the dimensional structure of this, it turns out that you can derive through symmetry and reasoning about the quantities that the frequency of those oscillations has got to be given by terms such as this one, this alpha times delta. It's these two here. If we have alpha and delta, they're both of units 1 over time. So multiplying them will be 1 over time squared, and taking the square root will yield something of 1 over time, which is what we need for the frequency of oscillation. And this is indeed exactly the case. Another classic case of this is with a pendulum, and you're reasoning about the timing of the pendulum, what it's the period associated with it. And you can, on first principles, derive how it must depend on certain of the parameters of the system. Okay, so that's a very important use of dimensional reasoning, is sitting down and saying, okay, I'm trying to formulate this portion of a model, and maybe a system dynamics model, maybe an agent-based model. What are plausible formulations given the dimensions involved? What are consistent formulations? After all, the formula you put in there, even if it's an agent-based model, the formula you put in, to characterize the probability of deciding this or that has to be dimensionless. So it can help you arrive at consistent formulations within the model for certain types of formulae. Okay. A final thing I'm just going to allude to is the fact that one of the most powerful uses of this sort of reasoning is one that might be unexpected. And that has to do with the fact that we can greatly simplify a model through use of this information. By simplify, I mean reduce greatly the number of parameters, perhaps to bring the model down from 5 parameters to 2 or to 3. And one of the reasons this is most important is because if you're trying to calibrate that model, or you're trying to parameterize it to arrive at, or you're trying to do sensitivity analysis on those parameters, having fewer parameters makes it a lot easier, okay? And there's a famous theorem. It's called the Buckingham pi theorem. And basically what it says is that if we have a model that's dimensionally consistent, if we have a model that's sensible in the sense that we're only adding together quantities of the same dimension, we're only doing things that are consistent dimensionally, we can always rephrase it into a dimensionless form. We can always rephrase it in forms that use only dimensionless quantities, that use only quantities which can be expressed without depending on unit systems. And this again has to do with the fact that the world out there has to be, the processes in the world have to be amenable to some sort of description that is dimensionless, because the world does not change its behavior as we change unit systems. Okay? And the Buckingham pi theorem demonstrates mathematically that this is true. But the important point is not only is that the case, that yes, we can reformulate consistently things described in the world in a dimensionless fashion, but the fact that if we do so, if we rephrase them in a dimensionless fashion, we can do so with fewer variables. We can actually simplify it. We can make it much simpler. We can actually strip out unneeded complexity for it. Okay? So we can take out, and again, go down from something like 5 parameters to 2 and perform calibration more easily. Put our efforts into estimating fewer parameters, etc. And it turns out that this is foundational for some of the other uses of dimensional analysis, including the ability to formulate scale models. Models that are smaller, involve far fewer agents, but give great insight into how that would behave with much larger numbers of agents. Okay. It's also of great help for sensitivity analysis and calibration. And it turns out that in order to identify the dimensionless variables, it's a fairly straightforward exercise. And it begins with what's called a dimensional matrix. And you can systematically manipulate this matrix to arrive at a formulation which involves fewer parameters and they're all dimensionless parameters. They're all parameters which don't depend on unit systems. You don't have to worry whether the data was measured in seconds or milliseconds. You don't have to worry if it was measured in meters or in feet. The model is independent of that. Okay, and it turns out that, without going into it, this is key for reasoning about how a model with smaller populations would behave when compared with a model with larger populations. So the idea being, if we don't have a computer that's large enough to simulate all of the population of Canada, we can perhaps run it with 20,000 people, but still have principled insight to how it would behave with a much larger model. And this is the notion of reduced scale models. Okay, that's more advanced material. I may cover that at some point in an advanced modeling class, but for now it remains outside the coverage of this lecture, and indeed, ladies and gentlemen, outside the coverage of this course. So it's with considerable regret that we're going to be drawing the lectures for this course to a close. There's a lot more material to cover. I had hoped, but fell short of the possibility of delivering a lecture on frontiers of modeling today. And you'll find lectures of that sort from me online, where I talk about many of the most exciting trends in modeling. These go from talking about combinations with machine learning methods, models that automatically recalibrate as new data comes in and learn from the new data, to issues having to do with modeling languages that are much more expressive, that allow us to characterize a model in agent-based modeling with the economy of specification that we can use in system dynamics modeling, and with the mathematical precision of that, rather than relying on languages like Java to do our characterization of agent dynamics. New vistas as well in terms of collaborative modeling tools that can be used like Google Docs by people from around the world at the same time for interacting around a model, people from very, very different backgrounds. Combination of models with big data is one of the areas I'm most excited about. The fact that increasingly we have recourse to data at a micro behavior level about aspects of the environment and people that we can use to inform our models. And the use of models as learning tools so that we're refining our thinking as new evidence comes in, and we can use our model to advance our thinking and advance the thinking of teams. It's a time of great opportunity when it comes to models. And the sorts of skills you've developed in this class, well, no doubt at times painful to develop, are types of skills that are in very high demand. We're happen to be fortunate to be one of the centers of modeling worldwide that actually trains large numbers of students in platforms like AnyLogic, which are in very high demand in certain areas. And we have a lot of individuals who come here to this university every year, in this very classroom, in fact, every summer, to learn some of these techniques and to try to find partners. And quite a few of them go to partner with students, hiring them as consultants, or bringing them for internships, or hiring them after graduation, or what have you. So if any of you are interested in this sort of modeling, and I know it's not for everyone, but if anyone is, there's certainly a heck of a lot of opportunities here on campus, and in fact globally, with the connections that extend from the campus for doing this sort of work. Simulation models are an important part of the current landscape. Sometimes they run in hidden ways outside of your view, such as in a car's control system. Sometimes they are used very explicitly for decision making. But over the course of your professional lifetimes, I expect to see them increasingly integrated, not only with decision making, but with the sources of data that are coming in. You'll sometimes hear models used as an alternative to data. It's far from the truth. It's really their combination together. The ability to capture an understanding of process like we've been capturing in models, whether in agent-based system dynamics or discrete event modeling, and to combine that with evidence in the form of new data. That's really where the action's at these days. And there's a huge imbalance between supply and demand, with much more demand than there is supply of people to address it. So I commend you for your attention in class. I have tried to give a glimpse here of a very deep and substantive area. And I know I've fallen short in certain ways of sort of helping you see some components. But it's really been an honor and pleasure to work with you this semester. And I'm looking forward to seeing many of you in coming weeks for review sessions and for the remaining office hours this afternoon. So, if any of you over the next few weeks, beyond those pre-scheduled things, and we'll be working with Doodle to schedule 1 or 2 review sessions and sample questions I'll be giving out for the exam. If any of you need to meet outside of that, please email me, and I'll see if maybe we can have some office hours beyond the end of the semester, okay? Today's office hours, because of the adverse air quality, Although I note this is now blowing somewhat cleaner air on me, which is welcome. I'll be holding office hours at my office rather than again here. Sometimes being in this building has made me dizzy in recent weeks. So I'd be glad to see you for office hours. So thank you very much for your attendance. Thank you very much for your participation. And I'll look forward to answering any remaining questions. One final point about that final assignment. It has an immediacy to it, which I'm sure all of you realize. I did post a new version. I want to emphasize this. I sent mail, but some may have missed it. I posted a new version of the assignment, which in red indicated a bunch of clarifications that came out of multiple meetings with students and that I thought could be useful in pursuing that problem set. If you haven't seen it, I would urge you to take a look at that just because it may at the least confirm some of your understanding, or it may give you those key understandings you need to finish that off, okay? But otherwise, thank you very, very much. Appreciate all your attention, and I'll look forward to seeing you in coming weeks and then on the final. Thanks. Thanks so much. Thanks so much.